Now, see a mutual inductance of two long coaxial solenoid. Suppose you have taken here, this is the solenoid 1. We can take as this is S1. There is another solenoid here, like this. This is here S2. Now, we can write N1 is number of turns, N1 and N2 are number of turns per unit length in solenoids S1 and S2. R1 and R2 are radii of solenoids, and here R1 is greater than R2. So, these are, we have taken the parameters. Length for the solenoid is only, that is we have taken L, that is common for both. So, suppose current I1 is flowing through the solenoid 1, that is a variable current. So, when variable current I1 flows through the solenoid S1, then magnetic flux linked with the solenoid 2 is equal to M21 into I1. Because the magnetic flux linked with the solenoid 2 is directly proportional to current flowing through the coil 1. So, that can be written phi 2 is equal to M21 into I1. Phi 2 is the magnetic flux associated with the solenoid S2. Now, we can also write magnetic field in coil 1. Magnetic field in coil 1 can be written B1 is equal to mu naught N1 I1. So, total magnetic flux linked with the solenoid 2 is, that can be written phi 2 is equal to B1 into A2 into number of turns into total number of turns in the coil S2. Put the value of this B1, that will be coming here mu naught N1 I1 into A2 into N2 L, where A2 is the area of cross section of the solenoid S2. So, you have calculated these two. So, now you can equate these two flux. So, you will be getting, when you are going to equate these two, you will be getting here M21 I1 is equal to, in this case, mu naught N1 N2 I1 A2 into L. I1 cancel. So, you can write M21 is equal to mu naught N1 N2 pi R2 square into L. So, this is the mutual inductance of the coil 2 with respect to coil 1, and see here that depends on basically the geometry of the coil, and also here geometry of the coil, that includes the radius as well as the number of turns. Another one also, it depends on the orientation of the coils and also the distance between two coils. So, these coils are placed such that the one coil is inside it. So, there is no possibility of the leakage of magnetic flux, so the maximum induction takes place. So, this we have calculated mutual inductance of the coil 2 with respect to coil 1. Similarly, we can calculate mutual inductance of the coil 1 with respect to coil 2. Suppose current I2 flows through this coil 2 and there is no current in the coil 1, then the magnetic flux linked with the coil 1 with respect to 2, that is equal to M12 into I2, current flowing through the coil 2. And now, total magnetic flux linked with the coil 1 is equal to, we can also write phi 1 is equal to mu naught N2 I2, that is magnetic field in the coil 2, which is common for the coil 1 also, into, now area of the coil 2 only will be included, that is A2, because we take only the common area which is in both the coils. So, this much area is included here, whether the current is flowing through the bigger coil or current is flowing through the smaller coil, that is equal to here N1 into L, And now when we equate this thing, we will be getting M1 I2 is equal to here mu naught N1 N2 I2 A2 into L, and now I2 will get cancelled. So, M12 is equal to mu naught N1 N2 A2 into L, and here we can write M12 is equal to M21. So, this by this way we can calculate mutual inductance related with these two coils of the, that means the coil of, mutual inductance of coil 1 with respect to another one, and just by using the concept of the magnetic flux, and similarly this one is the mutual inductance. Now, see here we have seen separately mutual induction and self induction. We have calculated mutual inductance of the solenoids and also we have calculated self inductance. Suppose you have taken two coils like this, and in both the coils current is flowing. Here the another coil is over here. In both the coil current is flowing simultaneously. Suppose there is a current I1 and there is the current I2. And if you are getting the total magnetic flux through this coil, or you can say EMF induced in this coil 1, we can write here EMF in the coil 1 can be written minus LdI1 upon dt, that is due to self induction in this coil, and also due to the mutual inductance of induction of this due to this coil, that is here M12, that is dI2 upon dt. So, this is the total EMF induced in coil 1. Similarly, we can calculate the total EMF induced in coil 2 here. So, this is the case where mutual inductance and mutual induction and self induction are considered together.